Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, so we just took the equilibrium condition, the moment equilibrium condition, and we arrived to this relation. That means the cross shear is equal, right? Tau yx is equal to tau xy. Similarly, tau xz equal to tau zx, and so on. So, if you get the cross shear which are equal, then basically the 9 components will come down to 6 components basically, right. So, you need 9 stress components to define the state of stress at a point, already we have seen in the last lecture. So, the 9 components, 9 stress components will come down to 6 stress components if you consider this equality of the cross shear. So, that is the biggest advantage, because from your 9 unknown components, unknown stress components, now it is coming down to the 6 unknown stress components, right, and that is the biggest advantage of taking or considering this equilibrium condition. Now, in case of 3 dimensional state of stress, basically you need 6 stress components to define the state of stress, whereas as I told you, as we discussed in the last lecture, the plane stress condition, right. So, in the plane stress condition, now your unknown stress components are 3. So, sigma x, sigma y and tau xy if the state of stress in xy plane, right. So, now if you similarly if you consider the force equilibrium, that is Fx equal to 0, that means all the summation of all the forces along x direction is 0, then basically you will be getting. So, if you come back to this figure basically, so first we identify what are the forces are acting in x direction. Okay. So, let us start from the negative x phase. So, this sigma x is acting along x direction on negative x phase. This sigma x plus del sigma x del x delta x, that is a variation in sigma x, which is acting on positive x phase, that is also acting along x direction. Similarly, this tau yx on y plane, on say negative y plane. Now, I mean as per our discussion, now it is very clear that tau xy is equal to tau xy tau yx. So, therefore, this is also acting along x direction, and this is also acting along x direction. So, these are the stress components which will cause the force in the x direction. So, let us write down those. So, sigma x plus del sigma x del x delta x, and this is the stress acting on positive x phase, right, on which area? The area is nothing but del y del z, right. Okay. Similarly, this is the stress tau yx plus del tau yx del y delta y del x del z. So, this is the force acting on positive y plane along x direction. So, these two forces are along the positive x direction, right. So, other forces which are acting along negative x direction are sigma x del y del z plus, so this will be minus, sorry. So, this will be minus tau xy, or rather tau yx, let us write down the actual thing. So, tau yx del x del z equal to 0. So, these are four force components, okay, which are acting along x direction. Okay. So, if we simplify this thing, we will be coming to this del sigma x del x del x del y del z plus del tau x y I can write, because tau y x equal to tau x y, already we have established this relation. So, del tau x y del y into del x del y del z equal to 0, right. So, we can further write del sigma x del x plus del tau x y del y into del x del y del z equal to 0, right. Since your del x del y del z cannot be equal to 0, because you are considering one parallelepiped around point O. So, they cannot be 0, right. So, the multiplied, because you are considering some finite volume of the parallelepiped. Okay. So, if that is not 0, then of course, this must be 0. So, del sigma x del x plus del tau x y del y must be 0. So, this is one important relation. So, this is equation say 1. This is the important relation which has been established by considering the equilibrium condition along x direction. So, if you perform, or if you exploit this equilibrium condition, so you will be coming to this relation. So, your stress, if you say this body is under equilibrium, your stress cannot be arbitrary. So, they should should have some proper relation, and that relation is established by this equation 1. Okay. So, del sigma x del x, that is a derivative, partial derivative, plus del tau x y del y. Okay. The summation of these two must be 0. Similarly, if we try to establish the equilibrium condition along y direction. So, in a similar fashion, if we take f y equal to summation of f y equal to 0, then what we will get? We will get, so first let us come back to this figure again. What are the forces? Let us identify what are the forces are acting along y direction. So, starting from say negative x phase. So, this tau x y is acting along y direction. Okay. This sigma y plus del sigma y del y delta y is acting along y direction, which is acting on of course positive y phase. Similarly, sigma y is acting on negative y phase, which is acting towards y direction, and this is the stress tau x y plus del tau x y del x delta x, that is also acting on positive x phase, but along y direction. So, these are four, say these will constitute four force components which are acting along y direction. So, very similar to the previous operation, if we perform. So, we will get sigma y plus del sigma y del y delta y del x del z plus tau x y plus del tau x y del x delta x del y del z minus sigma y del x del z minus tau x y del y del z. Now, if we perform the similar simplification, then we will finally get del sigma y del y plus del tau x y del x equal to 0. So, we have got another relation which is considering sigma y and tau x y, okay, and this relation again is required to get the equilibrium condition of the system. Okay. So, your stress components should follow these relations. Okay. So, I mean this is nothing but these two, equation 1 and equation 2 are nothing but the equilibrium equations, okay, required for your plane stress condition. Okay. So, now if you look at these equations, we have not considered the body force. Now, body force may happen and it is a pretty common thing, right. So, if you consider the body force, that means if you consider the gravitational, that means the weight, or the, I mean in case of civil engineering we generally get the seepage force or inertia force or something like that. So, if you have the body force, then you need to consider the body force into account. So, if you consider the body force into consideration, then what exactly you will be getting? So, if there is body force in say x direction, then you get this equation 1 will be modified as del sigma x del x plus del tau x y del y. Up to that we have derived already, plus this body force term depending on the direction of course, okay, must be 0. So, this is the extra term which will be coming into the picture due to the consideration of body force. Okay. Similarly, I am not writing this thing again, but similarly this equation 2 will be modified del sigma y del y plus del tau x y del x plus y, where y is the body force along the y direction. Okay. So, if you have the body force in x and y direction, so basically these equations of equilibrium will be modified by considering the respective body force. Okay. Now, if you try to, I mean we are not going to derive that thing, but you can, we are just following the same procedure and same same steps involved in obtaining these equations. If we follow for the 3-dimensional state of stress, then basically that will consider or that will reveal the following equations. So, for 3D state of stress, your equation 1 will be modified like that, del tau x y del y plus del tau x z del z plus body force term equal to 0. Is that clear? So, if you consider 2-dimensional state of stress, then basically this first term and second term were coming, already we have derived that, right. But once you are considering the 3-dimensional state of stress, so this is the extra term which will be coming for the consideration of the z direction. Okay. So, this is nothing but the equilibrium equation for 3-dimensional state of stress. Similarly, so this will be coming when you are considering the equilibrium say conditions, that is summation of f x equal to 0. Similarly, if you consider summation of f y equal to 0, so this equation 2 will be getting modified by considering another term say tau y z, okay, and so on. So, you will be getting 3 equilibrium equations by considering the force equilibrium along x direction, along y direction and along z direction. That means summation of f x equal to 0, summation of f y equal to 0 and summation of f z equal to 0. Okay. So, we are not going to derive that thing. So, you can get or you can derive this thing by your own. Okay. So, let us talk about some new concept. Okay. So far whatever we have discussed, based on that some new concept we are going to discuss, that is, if you know the state of stress in xy coordinate system, right, if you know the state of stress in xy coordinate system. So, still we are talking about the plane stress condition. Okay. So, as I told you, so in this particular course we will be mainly confining ourselves or restricting ourselves in the calculation or in the analysis of plane stress condition. So, if you know the state of stress at a point, okay, based on xy coordinate system, that means if you know the state of stress in xy coordinate system, that means what are the stress components are known to you? 3, sigma x, sigma y and tau xy, and since tau yx equal to tau xy, so that will come to one common stress components. So, you suppose you know sigma x, sigma y and tau xy, that means you know the state of stress in xy coordinate system. Can I define or can I get the state of stress in some arbitrary coordinate system, okay, if I know the orientation of that coordinate system with respect to the xy coordinate system? So, what did I mean? Suppose this is your xy coordinate system. This is your xy coordinate system. Okay. Now, another coordinate system you are considering, say x prime, y prime, which is making, this is known to me, which is making an angle say theta with respect to x axis. Okay. Now, I know the state of stress in xy coordinate system, that means I know sigma x, sigma y and tau xy. So, this is known to me. So, if that is known to me, can I find out the state of stress in x prime y prime coordinate system, that means sigma x prime, sigma y prime and tau x prime y prime. So, if I know this, can I get this? This is my question. So, if I, so we'll try to prove that yes, if I know the state of stress in xy coordinate system, I will be getting any arbitrary oriented coordinate system x prime y prime, okay, where the state of stress can be defined in terms of sigma x, sigma y and tau xy and the orientation angle theta. Similarly, if you define another coordinates, another arbitrary coordinate system, say x double prime, y double prime, and say this angle say theta double prime. So, by knowing sigma x, sigma y and tau xy, can I get sigma x double prime, sigma y double prime and tau x double prime, y double prime? Yes, we can get it. So, that is my objective. So, by knowing the stress components in one coordinate system, can I get the stress components in other coordinate system? So, that is my objective. Now, let us talk about that thing now, and this is very much required. I mean, if you deal with any system, any mechanical system, right, whether it is civil engineering system or aerospace engineering system or mechanical engineering system. So, wherever you go, basically you know, suppose you know the boundary condition and you know the state of stress, okay, in some coordinate system, and you want to find out how much stress is getting developed if you rotate the axis, okay, on some different plane. If you want to find out the stress components, how you will find out? So, it is very much required, that is your stress components knowing in some arbitrary coordinate system. So, if I look at this figure, okay, this is one thin sheet or thin plate, whatever you say, which is under plane stress condition, which is under different externally applied forces F1 to Fn. Okay. This is your xy coordinate system, because z direction we do not have the variation, because this is the plane stress condition as we know. Okay. So, in this situation we know the state of stress, okay, in xy plane. Okay. That means I know sigma x, sigma y and tau xy. So, these three things are known to me. Now, I am choosing one arbitrary plane, some inclined plane, okay, which is considering O as the center, and this arbitrary plane is defined by the, the plane will be defined by direction normal. So, this plane is nothing but your x prime plane, okay, and similarly y prime plane is also defined. So, that is along the plane. Okay. So, now what I am considering, I have the body and I am considering another plane, inclined plane, which is inclined by an angle theta. Okay. So, with respect to your x axis, your x prime axis making an angle theta, right. So, that means the angle between x and x prime axis is theta. So, I am defining one arbitrary plane x prime, that is defined here, okay, and y prime, that is another axis. Of course, the x prime y prime axis will be there. So, my objective is to find out from this sigma x prime, sigma y prime and tau x prime y prime. Okay. I hope you have understood the concept, why we need that. I know the state of stress in xy coordinate system. Now, I want to know the state of stress on some arbitrary plane, say x prime plane. Okay. So, for that you need these stress components, fine. So, let us do that. So, what I am doing, I am just considering this part and I am blowing it up, okay, and I am getting. So, this is my x prime axis, this is my y prime axis, this is the inclined plane. Okay. So, Mn is the inclined plane, okay, and whereas MP is your x plane and your NP is your y plane. Okay. Fine. So, I know the state of stress in xy coordinate system, I want to know the state of stress on x prime y prime coordinate system. That means, sigma x prime, tau x prime y prime and sigma y prime are required to know. Okay. So, now what we can do in this figure, if you look at. So, this figure if you consider, as I told you that when we are going to discuss this state of stress and all. So, each and every point of that system is under equilibrium. So, now in this figure whatever stresses or force, ultimately the stress will be multiplied by the area and you will get the force. So, that force will, all the forces together will satisfy the equilibrium conditions. Now, what I am going to do, I am considering the equilibrium condition along x prime direction and along y prime direction. What I am going to do? I am going to take, or I am going to satisfy the equilibrium condition along x prime direction and y prime direction. That means, summation of f x prime equal to 0 and summation of f y prime equal to 0. Okay. So, let us do that. So, if I consider this is 0, okay, that means the force summation of all the forces acting along x prime direction are 0. Okay. So, what are the forces are acting along x prime direction? So, that you will be getting from this figure. So, let us identify those stress components which will be causing the forces along x prime direction. So, first one will be sigma x prime, that is the normal stress acting on Mn plane, that is the inclined plane, okay, along x prime direction. Now, this sigma x will be having, the sigma x will be causing the force in x direction, but of course, I can take the component of that force along x prime direction. Similarly, tau x y, that is also acting on along, I mean along your this on this plane it is acting on along y direction, and this plane it is acting along x direction, right. So, I will be getting the components of that stress also. Okay. So, if I take all the components, so it will be coming like that. So, sigma x prime, okay, delta z into mn. This is the, so sigma x prime is the stress acting on x prime plane, and what is the area of the x prime plane? Mn, okay. This is the side Mn multiplied by delta z, okay. So, this is the area on which sigma x prime is acting, and that force is acting along x prime direction, okay. Similarly, sigma x is acting on x plane, right. So, sigma x, now what is the area of x plane? Delta z into mp, okay. What is that? So, this is your mp and this is your delta z. So, this is the area, this is the rectangular area on which sigma x is acting, okay. So, that is the force in x direction. Now, I have to take the component of this force along x prime direction. So, what to do? Simply multiplied by cos theta. So, I will be getting the component of that force along x prime direction. Similarly, tau x y into delta z into mp, right. What is that force? That is the force acting on x plane, right. That is the force acting on x plane along y direction. So, because this is because of this tau x y, right. So, I have to take the component of that. So, that component will be sin theta. Similarly, I will be getting sigma y del z into np. Please look at the figure, you will be getting this. So, this is the force acting on y plane along y direction. I have to take the component of that towards the x prime direction minus tau x y delta z into np and the component. So, these are all forces acting along x prime direction. Okay. So, this I am calling as equation say 1. Similarly, I am going to exploit this thing, f y prime summation of f y prime equal to 0. So, if I do that, what are the forces are acting? Del z into mn, okay. So, that is the force acting on the inclined plane along y prime direction. So, this is due to this component, okay, fine, minus plus rather sigma x del z mp and the component of that along y prime direction minus tau x y del z mp component of that cos theta minus sigma y del z np cos theta plus tau xy del z np sin theta is equal to 0. Say this equation is 2. Okay. So, I have got two equations, equation 1 and equation 2, by satisfying the equilibrium of forces along x prime direction and along y prime direction. Okay. So, I will stop here today. So, in the next lecture we will be taking these two equations and we will get our required solution. Thank you very much.